Acid-base equilibrium, Kb, Ka, pKa, and pKb. In this tutorial, we will be going over the general equation for weak bases, base dissociation constant Kb, categories of weak bases, the relationship between Ka and Kb, calculating Kb and Ka examples, and finally pKa and pKb. General equation for a weak base. This refers to the equilibrium in which a weak base reacts with water to form the corresponding conjugate acid and hydroxide ion. So if we look at this general equation right here, B is representing the general formula of a weak base. Hb plus 1 represents the general formula of the conjugate acid, as we can see that they differ only by a hydrogen ion. And OH minus 1 represents a hydroxide ion. Note, water is necessary to include in a weak base chemical equation as a proton source. These bases contain one or more non-bonding electron pairs, or lone pairs of electrons. The weak base must include non-bonding electron pairs to form a coordinate covalent bond, otherwise known as a dative bond, with the hydrogen ions. The equilibrium expression for a weak base is represented by Kb is equal to the concentration of the conjugate acid times the concentration of the hydroxide ion divided by the concentration of the weak base, where Kb is the base dissociation constant. The most commonly encountered weak base is ammonia. The chemical equation for ammonia is ammonia plus water produces the ammonium ion and hydroxide ion. The equilibrium expression for this equation would be Kb is equal to the concentration of the ammonium ion times the concentration of the hydroxide ion divided by the concentration of ammonia. Notice, water is not included in the equilibrium expression because it is in the liquid phase. Categories of weak bases. Category 1 includes neutral substances. These weak bases have an atom with a non-bonding pair of electrons that can serve as a proton acceptor. Oftentimes, this atom is the central atom of the molecule. These central atoms are frequently nitrogen and oxygen. So an example, here we have the structural formula for ammonia. We'll notice here that it has a lone pair. If we add a hydrogen ion to this, we will produce the ammonium ion, so that coordinate covalent bond is this bond right here. Another example is when water acts as a weak base. Notice that water has two lone pairs. When it accepts a hydrogen ion, it produces the hydronium ion. So again, we can see that coordinate covalent bond between the hydrogen ion and the water molecule right here. Category 2 is anions of weak acids. So for example, if we have the weak acid HCN, the conjugate weak base is Cn minus 1, and the Cn minus 1 ion has a Kb of 1.6 times 10 to the negative 5. Another example is HCO3 minus 1, which is a weak acid. Its conjugate base is the carbonate ion, which has a Kb of 2.1 times 10 to the negative 4. Relationship between Ka and Kb. The product of the acid dissociation constant for an acid, Ka, and the base dissociation constant, Kb, for its conjugate base is equal to the ion product constant for water, Kw. This is represented as the formula Ka times Kb is equal to Kw. As the strength of an acid increases, so a larger Ka, the strength of its conjugate base decreases, in other words, a smaller Kb, so that the product of Ka times Kb equals 1.0 times 10 to the negative 14, which is Kw. Kb can be calculated for any weak base if the Ka of the conjugate acid is known. Calculating Kb and Ka examples. So in our first example, we're going to calculate the Kb for the fluoride ion if Ka of HF is 6.8 times 10 to the negative 4. So we're going to start out with the formula Ka times Kb is equal to Kw. We're going to rearrange our formula to solve for Kb. So Kb is equal to Kw divided by Ka. We'll plug in our values. So Kw is 1 times 10 to the negative 14. Ka was given to us right here. So on the bottom, we're going to put 6.8 times 10 to the negative 4. And if we do the calculation for this, Kb is going to equal 1.5 times 10 to the negative 11. Ka can be calculated for any weak acid if the Kb of the conjugate base is known. So in this example, we're going to calculate the Ka for the ammonium ion, NH4+, if Kb of ammonia is 1.8 times 10 to the negative 5. So we'll start out with our formula Ka times Kb is equal to Kw. We'll rearrange our formula to solve for Ka. So Ka is equal to Kw divided by Kb. We'll plug in our values. 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. When we do our calculation here, we find that the Ka is equal to 5.6 times 10 to the negative 10. pKa and pKb. Acid or base dissociation constants are sometimes expressed as pKa or pKb. So pKa is equal to the negative log of Ka, and pKb is equal to the negative log of Kb. Therefore, pKa plus pKb is equal to pKw, which is equal to 14. The derivation of this formula starts with Ka times Kb is equal to Kw. If we take the negative log and distribute that with the Ka and Kb values, that will equal the negative log of Kw. Distributing the negative log gives us negative log of Ka times the negative log of Kb equals the negative log of Kw. Taking the negative log of these K values leads us to our formula of pKa plus pKb is equal to pKw. Note, the point of taking the negative log of the K values is to convert very small numbers into more reasonable numbers that are greater than 1. So what did you learn? We went over the general equation for weak bases, the base dissociation constant Kb, categories of weak bases, the relationship between Ka and Kb, calculating Kb and Ka examples, and finally pKa and pKb. Need more help? Feel free to contact me. Have a great day.